All right, we left off. We had gone through and showed that the time-independent Schrodinger equation in spherical coordinates can be separated out into two different equations: the radial equation, which we'll deal with next time, and the angular equation, which we're going to deal with right now. And so here's our angular equation. I just a little bit, I put one factor of sine squared theta over here just to clean up the left-hand side a little bit. And so this is, again, a partial differential equation where our goal is to try to find the function y, which is a function of theta and phi. And what we're going to do now is, again, try to find separable solutions. And so we're going to break this into two functions: a function theta, this is capital theta, that's only a function of theta, and a function phi, capital phi, which is only a function of phi. So we're going to place that into our function where we have y's and see what we get from there. So here, when I plug in my function, the phi will come straight through because it does not depend on theta, and so it just comes right out there. And I can write the rest of the equation like this. These derivatives are no longer partial because these functions are only functions of one variable now. So we can clean that up a little bit. And let's just try to be real careful that I indicate what's a capital theta and not. So this is our capital theta, this function here. And then over here, now the capital theta function will actually just go right through because it's not going to be affected by the derivative of phi. And so I get this capital theta here times the second derivative, this function phi, and then this equals our constant last time. So again, our constant is this L times L plus 1. We'll soon see why we decided to name our constant that way. Sine squared theta, and then just the total wave function I'll put over here. Now, our usual next step is then to divide by the wave function. So the wave function is this capital theta and this capital phi. And so I divide by that. I'll go through term by term. So this term here, I'll get rid of this phi and be left with a 1 over capital theta. So 1 over capital theta, sine of theta, d theta, and this piece is sine theta. So we see that this piece here, this term, only depends on theta, which again we're trying to head that way. That's our general procedure. And what I'm going to do is I'm going to pull this term over. So this term here, when I multiply or divide by 1 over theta phi, these guys will cancel. And so this term, when I bring it over, I'll get a positive sign, and then only have the sine squared theta piece. And finally, this guy, the theta will cancel, and I'll have 1 over capital phi times the second derivative piece here. And then this will equal 0. And then again, what we see here is we have this piece. So we have two terms in our function, or two terms in this differential equation. This side is only a function of theta. This side is only a function of phi. And so what our general procedure then is to say, well, each term separately must equal a constant. And the special constant we name this time will be m squared. So we'll call this equal to m squared, this equal to negative m squared. Again, the idea is, since you know that the function only depends on one variable and these add up to be 0, they have to equal a constant. So just to write this out a little bit cleaner, here are our two equations the way I just wrote it. So here what we'll do is we'll take this capital theta and kind of multiply it through, and so rewrite this equation this way. Again, I think it's a good idea, to go through these steps, at least once, just to make sure you follow how this is working. And so here we get rid of this guy, and then we have this L times L plus 1 sine squared theta times that capital theta function equals m squared theta function. And then down here we got this equation. So we got two differential equations, and now what we're going to do is go through and deal with these separately. So we'll start here with the equation of phi, because as you can see it looks a little simpler. And so let's start with that. So why don't you take a second now and see, so separation of variables has gotten us to this equation for capital phi. What is the solution to this differential equation? So go ahead and think about that. Okay, so let's look at this. If we take this equation, I can rewrite it as such. This is one of our basic differential equations in physics. All right, so we've got some function where the second derivative of that function is equal to a negative constant. And so this is our differential equation where the answer is some sort of oscillating function. We can typically write it as sinusoids. In this case, in quantum mechanics, it's going to be advantageous to write this in terms of complex exponentials. And so if you got something along these lines here, this would be the general solution of this differential equation. Now, first of all, I'm just going to say let's let m be positive or negative and just get rid of the negative piece here. And then what we typically do with these separable solutions is we're just going to, for now, we're going to put the some sort of a normalization constant on the other function. And so for now, we're just going to call this function e to the im phi. Again, m is our constant that we've been dealing with. And so this is our function that gives us the phi dependence. So we're getting there. We finally got one of these. And one thing we can look at is, so if you remember, when we write out our spherical coordinates, so this is our y and our x, and assume that the z is pointing out at you. Okay, if we have some vector r, then this phi is the angle here in this xy plane. And so you can imagine if I have my sort of thing here, and then I rotate all the way around by an angle of 2 pi, right, I should be right back where I started from. And so what we can say is that, well, we hope that this function would be like this. Okay, so that if I take this phi function at some point, phi plus 2 pi, it should equal what it was at that phi. So if I plug this into my equation, I get e to the im 2 pi plus little phi equals e to the im. We can cancel out the e to the im little phi, and we get e to the im 2 pi equals 1. So that requirement for this function to be single valued in the xy plane there is going to give us this particular relationship. And so let's think about that now. Okay, so what does that tell us about m? So think about this for a little bit, and we'll talk about it. All right, hopefully you got here that m is then going to be quantized to be 0, plus or minus 1, plus or minus 2, so on and so forth. And so if I got e to the im 2 pi, and I want that to equal 1, well, the trick, oftentimes with complex exponentials, one thing you can do is write it out into sines and cosines. And so this would be 2 pi m plus I sine 2 pi m equals 1. So basically, since this is the complex part, the sine function, we want basically what's going to work is whenever cosine equals 1. And so since this is a factor of 2 pi, this will just end up being 0, plus or minus 1, plus or minus 2, so on and so forth. And so this is going to be key. So we're going to use this to help us, again, in figuring out the full angular solution. So let's move on to the theta portion of the angular equation. So here's our differential equation. This is a bit more complicated, and so we're just going to explicitly write out the solution and then work with the solution and try to understand it a little bit better. The solution, so it's called the associated Legendre function. This a here is just a constant. And so this function, the definition of it can be written out this way here. So P, L, and M, these are orders in the equation, and this is what it's a function of. And so for us, it's going to end up being a function of cosine theta, but we'll just put it as x for right now to write out the formula. And so we got something looking like this here. And this thing here is the Legendre polynomial. Again, it's possible that you've seen this stuff before. And so this will end up being a polynomial of order L. For this equation to make sense for us right now, L is going to be a non-negative integer. And again, as we go along, we'll explore what L is. L is going to turn out to be pretty important. And the definition for this Legendre polynomial is as such here. Your textbook has these. Be careful. Some textbooks have slightly different definitions for this, and so you can oftentimes be off by a sign or something, a positive or negative sign. So if I put these two definitions together, here is our definition for the associated Legendre function. So if you're like me, this looks really scary at first. And so let's try to go through and unpack this a little bit and try to understand it, hopefully, a little bit better. And so let's look at an example. Let's take the associated Legendre function, L equals to 2 and M equals to 2 of some function x here. All right, and so if we look here, and so basically I'm going to put in a 2 wherever there's an m. So I get -1 squared. Down here, our L is a 2, so it's 2 squared, and then 2 factorial. So these are just constants. And here I get 1 minus my x squared, and then so to the 1 power there, so 2 over 2. And then here I've got a derivative of the m to the m plus L power, so it's going to be the fourth derivative. So the fourth derivative with respect to x of this guy here, which would be x squared minus 1 to the squared power. So even though this looks really scary, it's just a matter of plugging in the different numbers that you got there. And so if I was to say plug this in our particular case, so -1 squared just gives me a 1, and then down here 2 squared is 4 times 2, so I'd have an 8 downstairs. I have this 1 minus x squared piece on top, so I've dealt with the first two terms there. And now what I want is the fourth derivative of this guy here. So you can do this a couple different ways. Again, it's probably a good idea to go through and do this. But for me, so when you write this this thing out here, so I'll actually go through and just write it out. You know, it's easier, I think, to write it out in terms of actually taking that square there. So I'm just going to actually square x squared minus 1 and write those terms out. And so hopefully you can see that for the taking 4 derivatives, only this piece is going to survive that. And so if you just really quickly, if I start out with x to the 4th, my first derivative would be 4x cubed. My next derivative would be 12x squared. Next one, 24x. And finally, the fourth derivative would just be 24. And so when this is all said and done here, I'll end up with 1 minus x squared over 8 times 24, or 3 times 1 minus x squared. So, sometimes you'll need to use this formula for different homework problems, and sometimes you'll just be able to look whatever this function is up in a textbook or something. But another thing that we can do is we can use this formula for a little bit of physical insight. And so let's just, for instance, take this example. So we just did P22. So suppose I wanted to find P23. All right, and so here I'll just sort of say that it's equal. Now there's a couple of some constants, so we'll have something like the -1 to the 3 power 2 squared 2 factorial 1 minus x squared here. What was that going to be to the 3/2 power? But now, more importantly, if you look at this derivative, okay, we're going to be asked to take the 5th order derivative, will end up being the same thing in here. And so you can see that basically this has to be 0, and you can also argue that for anything higher than this, as far as m values, it has to be 0 as well. And so one thing that this formula tells us is that this guy here is equal to 0 for any m that's greater than the L value, which we're going to see, when we move forward in this chapter and sort of get more in touch with what L and M are. This is a really important consequence. I wanted to move on, and so at this point we've got these solutions that are going to turn out to be really important to us. And so we want to be able to interpret them a little bit. And so your book will have pictures such as this one here. And I just kind of wanted to go through this picture real quick, just kind of explain it, because it is, I think, when the first time you see it, kind of tricky. And so this is a picture where we're trying to understand a little bit better the associated Legendre polynomials, and in this case exactly L equals to 1 and M equals to 1. And so if we take our formula that we had, all right, and so please play along with this and make sure you can follow where I'm getting this. But when I plug into our formula, for this particular case here, I get something along these lines. And when I clean this up, I get negative 1/2 1 minus x squared to the 1/2 power times 2. And so altogether, negative 1 minus x squared to the 1/2 power. Now, to make this, again, a little bit more clear, so for us, we've been dealing with these polynomials as a function of x just to kind of get used to them. But when we're talking about the situation we're looking at with spherical coordinates, the associated Legendre polynomial is going to be a function of cosine. And so what that means is we just take that formula I just wrote and you write 1 minus cosine squared of theta to the 1/2. And in this case, this actually makes life easier because we can just say, well, this is going to equal to sine theta when I plug it in there. And so this is what they're plotting over here in this picture. And what they're basically saying is they're saying, look here, r is equal to the absolute value of the particular function that we're looking at, which in this case would end up just being sine of theta. So then on this particular plot here, we're plotting r equals to sine theta. So basically it's a polar plot where the length of the vector r, which we're given right over here, is equal to the absolute value of this PLM. And so we can see it at sort of different points. Like for instance, at this point here that they've drawn, I would say this is roughly the point theta is equal to pi over 4. So r equals to that value here. If you look over here, right, and so here at this point, again, this is our theta. This would be the point theta equals pi over 2, which, from this equation gives us r equals to 1, just like it shows there. And then it's sort of tricky to see, but basically over here, for instance, the value on the z-axis, so on the z-axis, that would be theta is equal to 0, which of course gives us r equals to 0. And so there is no length r. The same thing you could argue at this side over here. On this side, this would be theta equals to pi, and r equals to 0. So I think, we're going to find that just trying to visualize the angular solutions is tricky. And so we're just sort of starting down that path, and it's also made trickier in that, so what is this that we're looking at here, where this Legendre function is basically the angular part of our wave function. So to really get the probability density, we would need to square it, and really to get a complete picture, we need the other two parts, the r dependence and the phi dependence. But this gives us a pretty at least decent beginning to sort of understanding this here, and remembering that this particular function, this is not complex. And so basically the probability density would just be this function squared in the theta direction. And so in your textbook, you have pictures like these. So this is essentially what we just did, just for the first couple associated Legendre functions. And so I definitely suggest going through and making sure that this makes sense. And this is, our first step to understanding, or visualizing rather, the angular part of our solution. So just sort of concluding, we're looking at the angular equation today, and we went through and discussed a little bit about the solutions, which if you write out including normalization constants, look something like this here. So that's normalization constant. Here's the part that depends on phi, and then our theta dependence involves the associated Legendre functions. Just a note too that sometimes, so the phi dependence, this will sometimes be referred to as the azimuthal angle, and the theta will sometimes be described as the polar angle. And so these are very important, right? So first of all, we know that these are going to be the same solution for all spherically symmetric potentials. So these are going to be really important to us in three-dimensional quantum mechanics and in other facets of physics. We're going to spend a lot of time in the next week or so talking about these, exploring what's going on with these a little bit better. And so the first thing is, let's look here. This is just a chart of these actually written out. So again, it's similar to the Legendre functions. Sometimes you can go to the formula to figure it out, but usually if you're trying to use these, you'll just look it up in a table like right here. But here's basically the collection of these. And then here is the attempt to visualize this. And this is similar to what we did before. So here we're basically looking at a plot where R is equal to the absolute square of the particular spherical harmonic. So these things, these YLM functions, are referred to as the spherical harmonics. And so basically this is similar to that polar plot we were doing earlier. The one big difference is that this is the absolute squared, and that then this thing is then rotated about the z-axis. So the thing about this is, because we're taking the absolute squared, right, and if you remember, the functional component for phi is e to the I m phi, there will be no dependence on that angle. All right, and so you can see that here. And so basically, those polar plots, if you do it with the function squared, it changes a little bit, but still has similar features. And then those are essentially rotated about the z-axis is how you get these pictures here. We'll look at these again as we go on and understand more about angular momentum, and hopefully try to get a pretty good handle on these things.